last video, we talked about functions in general and how to tell whether a relation is more specifically a function because it's reliable. You can reliably predict an outcome from an input. So we're going to talk about more attributes of functions that you need to be confident about discussing about different scenarios or just mathematical representations of functions. So these are the questions you need to eventually be able to answer. The first one is the function continuous or discrete? And this is what those words mean. So if a function is continuous, the dots or the ordered pairs that make up the function, they get connected with a line or a curve. So if it's a practical scenario, then little tiny decimal numbers make sense in the context of the scenario. Now, a common error that students make is they think if the function ends, then it's not continuous. Because continuous, kind of when we talk generally, means it goes on or it continues forever. Not with functions. Continuous functions can end. They don't have to go on forever. They just have to be connected. So the thing that I want you guys to highlight here is the CON. Continuous, think connected. The other type of function is called a discrete function. And these are functions where there's separate dots. So each ordered pair is separated. So those dots are never connected. And if you have a practical scenario, the tiny decimal numbers don't make sense. So it would be like maybe you would have half a person in a practical scenario, or you could buy a tenth of a soda or something like that. So it's going to be things that that don't make sense, that make you have to graph this specific function with individual dots. So think discrete is dots, and that's what you're going to see. All right, the next thing that I want you guys to be able to answer is what is, in the context of the function, what is your independent variable as opposed to your dependent variable? So independent variable, it's very similar to what you've done in science classes before. The independent variable is what you change that then creates a change in something else. So in math, usually it's best to think about what is the input? What is the thing that changes first? What's the thing that happens first? What is the other thing that's changing dependent upon? So those are questions that you can ask yourself, and we'll talk about that in examples on the next page. The dependent variable, again, like science, this is the thing that changes. It's the thing that you can measure. So this is the output or the outcome of whatever happened with, or whatever change was made in the independent variable. It's the thing that happens second, or it's the thing that depends on the other variable. So next is domain and range. So the domain is the list, or sometimes it's not like a list of like numbers separated by commas. Sometimes it's an interval, like interval notation, or an inequality that shows that it includes all the numbers between two quantities. But the domain is the list of all possible x values for a function. And the range is the opposite. It's a list. Sometimes you can write it as just numbers listed off by separated by commas, or you can use an interval or an inequality to show a range of numbers. But range is referencing all of the possible y values for a function. All right, now domain and range are going to be specifically listed based on whether your function is a discrete or a continuous function. So remember, discrete functions are dots. So when you describe the domain and range of a discrete function, you're going to end up listing numbers off with separated by commas. But if you're dealing with a continuous function where you have a line or a curve, then you're going to be able to list the domain and range as an inequality using set builder notation, or an interval using interval notation. So a tip is, or an acronym that I use, is Dixie. So a lot of the terms we used on the first page have very similar, almost exactly the same meanings. So all of the things that have similar or the same meanings are in that first bubble and correspond to the word Dixie. So D stands for domain, I stands for the input. Input value is the x value. The domain is all of the x values. So x value, and the x value also corresponds with your independent variable. For roidy, so the R stands for range, the O stands for the output, the Y is the Y value, and DE is your dependent variable. So all the things that are associated with the word Dixie are associated with x values, and all the words associated with roidy are associated with your y values. So let's do some examples. Now what we're going to do on this next section is we're going to graph each of the functions given, and we're going to answer the questions. So we're going to answer whether it's a continuous or discrete function. We're going to identify the independent and dependent variables, and then we're going to identify the domain and the range. So for this first function, it's going to be represented by just a list of ordered pairs. So let's go ahead and plot those ordered pairs. So we've got -3, 2. We've got -1, -4. We've got 2, 0, and we've got 3, 5. So those are the only ordered pairs that exist on that function. If we were to connect those dots, what we would be communicating is that all of these little individual points that would be along that line or curve are included in this function. But the way the function is written, it's only including the ordered pairs listed. Now, this is not a super common function to see, but if you do see a function that is represented just by ordered pairs, then don't connect them. So what does that tell you? It tells you, for number one, that this is a discrete function. So the second thing is, what are your independent and dependent variables? This is a little bit of a lame question because there's no practical scenario involved. So all you would have to say for the independent variable is that these are all of your x values, and your dependent variable would be your y values. All right, and then finally, let's do our domain and range. Notice it's discrete. If it's discrete, you're going to list the domain and range as just a list of numbers. So you can just write it like this. I don't really care if you put the curly brackets or not, but what we're going to do is we're going to just list off all of the x values. So -3, -1, 2, and 3. For the range, we'll do the same thing, except now we're doing the y values. So 2, -4, 0, and 5. Sometimes you'll see that those rearranged from smallest to largest order, but I don't care so much. All right, so let's go on to example 2. Now we're given an equation. So let's create a t-chart. And we're not given any restriction on what x can be. So my suggestion is to plug in -2, -1, 0, 1, and 2. We're going to plug in a -2 for x. So we would have -5 times -2 plus 3. So -5 times -2 is +10. 10 plus 3 is 13. Then -5 times -1 plus 3, that would be +5 plus 3, which is 8. Then again, we'll do -5 times 0, that's 0, plus 3 is 3. -5 times 1 is -5, plus 3 is -2, and -5 times 2 is -10, -10 plus 3 is -7. So now what we can do is we can plot those points. So I've already done that here. All the points are plotted, and as it looks right now, this is a discrete function, but we need to think about whether it should stay a discrete function. I want you to go back to that original function rule, and notice all you were given was an equation. You weren't given any restriction for what x could be. Now, here's the key. You need to remember that the table is just a sample of some of the points along this line. So don't go based on the table for deciding whether a function is discrete or continuous. The reality is I could have plugged in 0.00000001 and found a point, and it would have been a legitimate point. So what that tells us is even though when we initially graphed it, we graphed it as individual dots, we need to go ahead and connect those dots with a line. And not only do we need to connect them, but we need to make sure we put arrows to show that we can put in an infinitely small number for x, and we can put in an infinitely large number for x, and it would be a valid number. So for our questions, the first one, is it continuous or discrete? This should be continuous. For 2, what is our independent and dependent variables? Anytime it's not a practical scenario, your independent variable is always your x value, and your dependent variable is always your y value. Now let's do domain and range. So I want you to think about, for domain, it's all of the possible x values. So think about it. What are all the possible numbers you could have put on the table? Like what I said earlier, you can go all the way to -infinity and all the way to +infinity. So set builder notation for this, you would put all real numbers. There's so many different ways you could say this. You can use the symbol for all real numbers, which is an R with double lines on the back. You could say that it's -infinity is less than x, which is less than infinity. That would work. Or if you want to do interval notation for this, you can put -infinity to +infinity to show that x could be anything. Now let's look at y. So think about the y value is how high or how low the graph can go. And it's going to go up forever and ever and ever and ever in the positive direction, and forever and ever and ever and ever in the negative direction. So our range is almost identical to our domain. So I'm going to go ahead and copy it, because our range is also all real numbers. You can use the symbol. You can say -infinity to +infinity. The interval would be the same. The only thing you need to change is that now when we're dealing with range, we need to use a variable of y. All right, let's go on to a practical scenario. So John has $3 in his piggy bank. He earns $2 every Monday for allowance. How much money Y will John have after X number of Mondays? So let's do a T-chart for this. Some of you, again, will intuitively know what the function rule is for this. If you don't, it's okay because we're going to try to find one. So let's just say at the very beginning, after no Mondays have passed, he already has $3 in his piggy bank. Let's say one Monday has passed. So he's going to have the $3 he started off with plus $2 more. If he's had 5 Mondays. So he's going to be making $10 more. Well, how'd you get that? You start off with $3 plus 5 plus 2 times 5 Mondays. If it were 10 Mondays, it would be $3 plus 2 times 10. And eventually, if there are X Mondays, then it would be 3 plus 2 times X. And that's going to give you your Y value. So for your function rule, you would say Y is equal to 3 plus 2x. Now, if we actually figured out what these y values were, that first line is already done. It's 3. The second line would be 5. The third line would be 10 plus 3, so 13. Then 3 plus 20, so 23. And then that's enough for us to plot some points. So let's go ahead and do that. So 0, 3 is our first point. Then 5, 13 is our next point. And then 10, 23. Okay, so let's talk about this. So far we have only 3 points plotted. I guess I could have plotted 1, 5. So we have 4 points plotted, and so we need to ask ourselves, are there more points? Are those points going to stay points? Or are they just going to be dots? Or do we need to just connect all those dots with a line? And here's what you want to ask yourself. So we need to think about what our X and our Y means. And it actually tells us for this one. X is the number of Mondays, and Y is the amount of money. So we're going to ask yourself, can you have 1.5 Mondays or 1.2 Mondays? And hopefully you're thinking that that doesn't make a whole lot of sense. So what that tells us first is that it's not continuous. It's going to be discrete. So let's go ahead and fill that out. So let's go ahead and fill in the rest of our dots. I want you to notice what happened here. You went up 2 boxes and then over 5 boxes, which is really up 2 over 1 because the scale on the x-axis is a 1. So let's just continue that pattern of going up 2 over 1 or up 2 over 5, however you want to look at it. So up 2 over 5, up 2 over 5, up 2 over 5, and we will continue until we have a really nice graph. Let's talk about independent and dependent variables. The independent variable, remember, independent variables go with our x values. So our x value here means the number of Mondays. So there's your independent variable. Your dependent variable is always your y value, so it's the amount of money that John has. Now let's talk about domain and range. Here's the deal. There's no end to this necessarily. So we could put an arrow on the end of that to show that it keeps going forever. So you can't physically list off all the possible ordered pairs for this. So this is how you're going to do it. So for our domain, the first thing we know is we're going to have to list numbers separated by commas. But what you can do so you don't have to list 1,000 different numbers is you're going to start with the first couple. So you can have 0 Mondays, 1 Monday, 2 Mondays. As soon as you've established a pattern of how the numbers are moving, you can put ... to show that it's going on forever. You can say ... to infinity if you want to, but just ... tells me that you're going to be counting up by ones, but it's going to go on forever. Now your range, let's talk about range. Notice what's happening with your range. As your number of Mondays goes up by 1, your amount of money, or John's amount of money, goes up by 2. So when 0 Mondays had passed, John had $3. After the next Monday, he had 5. After the next Monday, he had 7. And notice we've established a pattern that we're starting with 3 and we're counting by 2s. So now we can just say ... to say that it continues going on like that. All right, let's go on to example 4. Anja is filling her 48-gallon fish tank with a water hose. If the tank currently has 12 gallons of water and the hose adds 3 gallons of water per minute, what is the volume of water in the tank over time? So there's one thing about example 4 that's different than example 3. It doesn't tell us what our x and our y values are. So what I would suggest doing in the very beginning here is identifying what your independent and your dependent variables are. So here's a couple things to think about. Look at the last sentence And a lot of times it gives you a clue as to what your two variables are. So notice it says, what is the volume of the tank over time? So when you think variables, think about things that are changing. The two things that are changing are the volume of water in the tank and the time. So then think about what happens first, or maybe what causes something else to happen. And hopefully what you'll think is, well, as time changes, the volume changes. Or you could say it like this: the volume of water in the tank depends on how long it's been running. Listen to that statement. The volume depends. That tells us that the volume is our dependent variable, so that's our y value. So volume is y, and so therefore the time is going to be x. So we can go ahead and fill out question number 2 and 3. So question 2 is the independent variable, and that's going to be the time. And if you want to put the units, you can say time in minutes. And then the dependent variable is the volume. And again, if you want units, you can put in gallons. All right, now that's going to help us with our t-chart. So we could do an x and a y, but it might be a little bit easier to do time and volume. And let's think about this. So at 0 minutes, the volume in the tank is 12 gallons. And then after 1 minute, notice it's adding 3 more gallons per minute, so it'd be 12 plus 3, so that's 15. And then let's say 5 minutes. Well, think about that. So if you probably or hopefully in your head you're thinking, well, then there's going to be 15 more gallons in there. Well, how did you get that? 12 plus 3 gallons times 5 minutes. And then 12 plus 15 is 27. And let's say 10 minutes. After 10 minutes, it's going to be 12 plus 3 times 10. So 12 plus 30 is 42. And I'm actually getting close to the tank being full, so I'm going to keep going. So let's say 12 after 12 minutes. So the tank starts with 12 gallons plus 3 more gallons times 12 minutes. 3 times 12 is 36. 36 plus 12 is going to give us a 48. So all of this information is super helpful. All right, so let's go ahead and plot those points. So our first point was 0, 12. So 0, 12 is going to be right here. And then 115, so 115 is here. And then 527, so 5, right there. 1042, and 1248. All right, so now we need to look at our data and ask ourselves, does this need to be continuous or discrete? So ask yourself the question, could, let's say, 0.005 seconds and a certain number of gallons of water, would that make sense in this scenario? So will this scenario cover that time? And will the tank have a certain like little fractional amount of gallons in it? And hopefully you're saying yes, that is legitimate and makes sense. So what does that tell us? It tells us that we can connect our points with a line. Now, the next thing we want to ask ourselves is, does that line go on forever? Well, hopefully you recognize that after the tank is full, the scenario ends. So instead of putting an arrow here, we need to actually have that line end. It needs to stop there. So does this mean that this scenario or this function is not continuous? It doesn't. Remember, continuous doesn't mean that it goes on forever. Continuous means that the little individual dots are connected. So here for question number 1, we're going to say this is a continuous function. All right, now let's go on to the domain and the range. Because the function is continuous, our domain and range can be written in inequality format or set builder format, or it can be put in interval notation. So let's think about our smallest and our largest x value. One thing that is sometimes helpful to do is to think about a box drawn around your data. So think the left side of the box is going to go right there, and the right side of the box is going to go right there. So then look at your x values. Remember, domain has to do with your x values. The smallest x value is 0, and which is less than or equal to all of our x values, and then it goes all the way to 12. Let's talk about what that means. So the scenario starts at time 0 and ends at time 12. So that is set builder notation for our domain. If we wanted to do interval notation, we would do the smallest number in the interval, which is 0, the largest interval or number in the interval, which is 12. 0 minutes is included because 0 minutes is in the scenario, and 12 minutes is also included. All right, so now let's do the range. So now instead of looking at the left and right side of your function, what you want to do is look at the top and the bottom of your function. So let's look at this. The bottom of our function is right here, And the top of our function is right here. Now think about the y values associated with those two lines. The lowest y value is, and you can look at it in your table, the lowest y value is 12. It's included, so it's less than or equal to y. And the highest y value, or think about it, the highest volume in the tank is 48. For interval notation, it's going to be very similar to the domain, but we're going to have 12 as our lowest number, 48 is our highest number, and both those numbers are included. All right, now we're going to actually refer back to the two practical scenarios that we did in the previous video. So the first scenario was about Louie and her $55 Juice Line gift card, and she's using it to buy $5 smoothies. We've already talked about this in terms of the fact that, yes, it is a function. We've already discovered what the function rule is, and we also talked about the fact that it wouldn't make sense to connect the dots. Now you have vocabulary for that. Because it doesn't make sense for you to connect the dots, this scenario or this function would be discrete. Now, for number 2, let's talk about our independent and our dependent variables. For practical scenarios, we can identify what those mean, and this one was nice because it gives us which one is our y value and which one is our x value. Dependent variables are always y and independent always x. So the independent variable is the number of smoothies that Louie buys, and then the dependent variable is the money remaining. Be careful, it's not the total money, it's the money remaining based on the way the question is worded. All right, now let's talk about domain and range. Domain is the left and the right part of the graph. So if we were to draw a box around our data, the leftmost side of our graph is here, and the rightmost side of our graph is here. So let's think about those numbers. The smallest number is 0, the largest number is 11. Now remember, because we're dealing with a discrete function, we can't do an inequality. We have to list off numbers. So what you're going to do is you're going to say the domain is, and here's how we're going to write it. We're going to start off with our smallest number, which corresponds with how many smoothies she buys. So she can choose to buy no smoothies at all. She could buy 1 smoothie. She could buy 2 smoothies. At this point, you've established a pattern. Now, we can't just say ... because that would communicate that she can buy an infinite number of smoothies. So what we need to put is that end number, which corresponds with this point right here, which is 11. That's the highest number of smoothies she can buy. Now let's talk about the range. Here, we're going to look for what is the lowest and the highest point on our graph. So our lowest point is here, and our highest point is here. Remember, it refers to the amount of money remaining on Louie's gift card. So the smallest amount of money that she'll have is $0. The next amount of money, we wouldn't say $1 because smoothies don't cost $1. So if she has 1 more smoothie remaining, that means she has $5 on the card and then $10 on the card. So notice here, we've established a pattern. So we can say ... And so now we can say what's the largest amount of money that Louie can have on her card, and that's the top part of your graph, which is $55 total dollars. All right, let's go on to the last example about Franklin and his road trip to San Francisco. I went ahead and, just for making this more of a real world situation, I added the distance to San Francisco because reasonably Franklin's going to eventually stop driving when he arrives. So the first thing let's talk about is whether the scenario would be continuous or discrete. On the last video, we did talk about whether it made sense to have all those in-between little points or not, and we talked about it making sense. So because of that, now we can add the vocabulary that this is a continuous function. All right, let's talk about our our independent and dependent variable, and we've been kind of told what they are. So our independent variable is always corresponding to the x value, so it's going to be the time in hours, and the dependent variable is going to be the distance in miles. And it's total distance here. It's not remaining miles or anything like that. All right, so now let's talk about the domain and the range. Because it's continuous, we can use an interval or we can use an inequality and do sub-builder notation. So let's talk about our leftmost point. It corresponds with the smallest amount of time, or the smallest number of hours in the scenario. Hopefully you can say that that is a 0. And then we can say it's less than or equal to x, which is less than or equal to, and then the highest number of hours he's going to go is, if we figured out the number, like how much time it's going to take to drive 1,200 miles, I've already done the calculation for you, and it's going to be off the graph here, but it's going to be over here, and it's 23.5 hours. So that's our domain. Now we can go ahead and write that in interval notation. Our smallest number in our interval is 0. Our largest number in our interval is 23.5, and both numbers are included. Let's go on to our range value. So our lowest range value is how far he had driven at the beginning of the scenario, and he had already driven 25 miles. So 25 is less than or equal to y, which is less than or equal to, and then the most miles he will drive is 1,200. And then in interval notation, we can go ahead and say 25 for our smallest, it is included, and 1,200 for our largest, and it also is included. Now, I just want to talk about this really fast. If I hadn't put if theoretically Franklin is going to continue driving past San Francisco and he's going to drive forever, then, and those scenarios happen where there's no end to it. So I want to talk about how that would change your domain and range. So what it would do is it would just take off this end part for the domain and the range. And usually you would say this backwards. You would say x is greater than or equal to 0 and y is greater than or equal to 25. And then for interval notation there, it would just be 0, comma, positive infinity, parentheses. And then for the range and interval notation, it would go from 25 to, again, positive infinity. So that's if theoretically he continued driving forever and ever.